When we think about major security flaws, we usually picture some hacker finding a single tiny mistake in the code. But what if the threat wasn't a mistake at all? What if it was being created by the very tools we trust to build our software, hiding deep inside the processor, completely in plain sight? Today, we're going to peel back the layers on a vulnerability that goes so much deeper than the famous Spectre attacks you've probably already heard about. Just let that sink in for a second. This is the conclusion from the actual security researchers at Tel Aviv University who dug into this. Shaky foundations. I mean, that's a genuinely terrifying thought when you realize that literally everything we do on our computers, our work, our private messages, everything, is built right on top of that foundation. Okay, so to really wrap our heads around this threat, we have to start with the incredibly powerful performance-boosting tech that's at the heart of it all. It's a feature inside every single modern CPU, and it's called speculative execution. Right, so think of your processor like a super fast, but really impatient chef. Instead of waiting for you to decide between carrots or onions for the soup, it just guesses you're going to want carrots and starts chopping them right away to save time. If it guessed right, awesome, dinner's ready way faster. If it guessed wrong, it just quietly throws the carrots away and grabs the onions. No harm, no foul. Or so we thought. That guessing game is speculative execution, and it's a huge reason why our computers feel so snappy. Now, the little brain behind this whole guessing game is something called the Branch Predictor Unit, or BPU. You can see a simple diagram of it here. It's a real piece of hardware that's job is to look at a program's history and predict which way it's going to go next. It's an amazing tool for speed, but here's the problem. Those predictions, they can be manipulated. When the first Spectre attacks hit the news, this is pretty much how everyone understood them. The classic example was tricking the CPU's predictor into running code that reads past the end of an array, bypassing a bounds check that's supposed to keep it contained. But it turns out that's not the whole story. Not even close. The classic attack, what you see on the left, is all about tricking the CPU into reading outside the lines. But the vulnerability we're talking about today, over on the right, is so much more subtle. It's called speculative type confusion. Instead of reading past some data, this attack tricks the CPU into getting confused about what the data is in the first place. It might see a number and treat it like a memory address. And the scariest part is, the weak point isn't some obvious security check. It's hiding in perfectly normal, innocent-looking code. And this brings us right to the core of it all. This isn't about an attacker finding a needle in a haystack. It's about the haystack itself just spontaneously creating needles. The original 2018 Spectre research paper actually nailed the fundamental issue perfectly with this quote. The attack makes the processor temporarily violate the basic rules of the program. It basically shows that the problem is so much broader than just checking the boundaries of an array. And here it is. This is the part that is genuinely chilling. This vulnerability doesn't have to be planted by a hacker. It can be created completely by accident by the compiler, the program that turns human code into machine code. Just by trying to make the code run faster, it can create a speculative type confusion flaw that the original programmer never intended and would probably never even be able to spot. So you might be thinking, okay, that's a scary theory, but is it a real-world problem? Oh yeah, it is. The researchers went hunting for these exact flaws inside one of the most important pieces of software on the planet, the Linux kernel. Let's open up their case files. Case file number 1, the eBPF system. So this is a cool feature in Linux that lets users run tiny verified programs inside the kernel. It's supposed to be a super secure sandbox. But the researchers found a huge hole. Its safety checks only looked at the correct path the program was supposed to take, not the speculative paths the CPU might guess. And that little oversight allowed an attacker to load a program with a hidden gadget that causes type confusion only when the CPU is guessing. And the result of that? Well, the attacker could build what they called a universal read gadget, which let them leak any memory they wanted from the kernel. We're talking the system's deepest secrets at a rate of 6.7 kilobytes per second with 99% accuracy, all from inside that supposedly safe sandbox. All right, case file number 2, the accidental flaw. This is that exact scenario we were just talking about. Step 1, a developer writes completely safe, normal code. Step 2, the compiler, trying to be clever and make things faster, decides to reuse a single storage spot for 2 different kinds of data. Step 3, boom! A hidden speculative type confusion flaw is born, because when the CPU guesses, it can get the 2 mixed up, and suddenly it's treating an attacker's input as a valid memory address. And what makes this even worse? The researchers discovered that the standard built-in Spectre defenses in major compilers from Microsoft and Intel were completely blind to this. They were all looking for that old bounds check pattern, and this new, more subtle flaw just slipped right past them. Finally, case file number 3, the performance trap. So, to fix some other security issues, Linux had to put in a defense that was secure, but really, really slow. To get that speed back, developers started using a bunch of faster checks instead, but this just created a brand new problem. Now the CPU could be tricked into speculatively calling the right function, but feeding it the completely wrong type of data. The researchers found dozens of these latent vulnerabilities just sitting there like time bombs, waiting for some future code change to make them go off. So when you look at all these case files together, the true scale of the problem really starts to come into focus. This isn't about patching a few isolated bugs anymore. What makes this whole thing so insidious is that trusted tools, our own compilers, can create the flaw. Programmers, actual humans, can't easily see it or fix it. A totally innocent-looking update can suddenly turn a harmless piece of code into a serious vulnerability. And all our current fixes, they're basically just band-aids on a crack in the foundation. Which leads us to a really, really tough question. If all these little spot fixes don't work, what does a real fix look like? And what is it going to cost us? Well, there is a comprehensive software solution that can block these attacks. It's called Speculative Load Hardening, or SLH. The way it works is actually pretty clever. It essentially freezes the results of any speculative action. The processor can still guess and do the work ahead of time, but it's not allowed to use the result of that guess for anything else until it confirms the guess was right. It stops the data leak before it can even happen. But that security comes at an absolutely staggering price. This chart here shows the brutal reality. Turning on SLH in the Linux kernel can slow down critical operations by up to 2.7 times. That's an average slowdown of 1.65 times across the board. In a world that is obsessed with speed, that is a massive, massive performance hit. And this just puts everyone in an impossible position. What do you choose, speed or security? I mean, can the giant data centers that power the cloud, or even the phone in your pocket, really afford to get that much slower just to protect against a threat that's super subtle and hard to pull off? And that really leaves us with one final big question to think about. Speculative execution is a brilliant trick that's given us decades of amazing performance. But it also created this ghost in the machine that we're now desperately trying to contain. As we keep building more complex, smarter systems to go faster and faster, are we just inadvertently building them on foundations of sand? Making them more powerful, sure, but also fundamentally more fragile?